Great, thanks so much for organizing the conference, Lev. It's been really great. I loved all the talks. And I'm very glad to be speaking here today in an Everettian universe in which this conference is taking place. In particular, I'm happy because this is one of the few audiences where it's relatively uncontroversial to acknowledge the existence of these other universes. For example, I assume that a majority of you find it uncontroversial that I am not the only one here giving this talk right now. There is an invisible version of me giving a talk very much like this one to invisible versions of all of you. Perhaps in some of these universes, members of the audience are disagreeing vehemently with my previous statement, whereas in others, it's so uncontroversial as to be basically boring. That latter group of people might have reached the exalted state that Lev Weitman and I aspires for us to be in, a state in which Everettian quantum theory has reached the mainstream. The universe that we actually inhabit is not quite that one. We have something in between these two extremes. Among Everettians, there's agreement on some basic facts of Everettian quantum theory, such as that there are other universes. While other parts of the theory remain controversial. For example, what is the role of probability in this theory? In the hope of bringing us closer to one of these exalted universes, I will be discussing one such controversial issue, like Charles, namely locality. So the issue I would like to address is the following. Are Everettian universes non-local, where a hint to the answer to the question has been given by the fact that I use scare quotes to denote universes, because I think this is a misnomer, as I will hopefully have convinced you by the end of the talk. So first of all, like Charles, I use Einstein's criterion of locality. That is, that the real factual situation of a system S1 is independent of what is done to system S2, which is spatially separated from the former. And I think people like Lev Weitman, argue that the world is not local in precisely this sense. So he writes in his Stanford Encyclopedia of Philosophy entry that although the many worlds interpretation removes most bothersome aspects of non-locality, action at a distance, the other aspect of quantum non-locality, the non-separability of remote objects manifested in entanglement, is still there. A world is a non-local concept. This explains why we observe non-local correlations in a particular world. So he answers my question in the negative. And there is something to this. There, for example, as I'll be arguing, the Schrödinger picture and the Schrödinger picture relative state formalism is not a local formalism. You can consider, for example, this entangled Bell state, where the subscripts denote to which qubit the state vectors belong, and where the values in the cats are the eigenvalues of the Z observables of the qubits. And like Paul Raymond Robichaud pointed out, we can perform local operations on one of these qubits, for example, the qubit on the left, which will introduce a relative phase, and that exact same relative phase would have been introduced by performing a similar operation on the other qubit. So these operations performed first on qubit 1 and qubit 2 seem to have the same effect on the real factual situation of the system. Meaning that if we identify the Schrödinger state vector with the real factual situation of those two qubits, then quantum theory would violate Einstein's criterion. There is a similar situation, so I have here, somewhat more elaborate, a setting where there's an observer, Alice, who is in a ready state and possesses these two qubits. She takes one and moves the qubit to some space-like separated region so that she's both spatially and dynamically isolated from qubit 1, as is represented by this dotted line here. So that should be imaginary, it's just here for illustrative purposes. After which she decides to measure qubit 2. And she says it was a 1 in one universe, and it is a minus 1 in another. So from her point of view, the qubit in the space-like separated region has now split. So I have these prime and double prime qubits. They denote the different instances of the qubits in both regions, because Alice doesn't see the full qubit anymore, she sees only part of it. And it seems like during this measurement, the qubit on the other side has split. So if we move to a relative state, the state relative to which Alice saw it was a -1, then that is a slightly different state for qubit 1. It is qubit 1 double prime. So here's a summary of what happened. Alice was in a ready state, she measured, and then these relative states appear to affect the state of systems in space-like separated regions. And more generally, if we have some universal state vector, which represents all systems in the universe, then that state vector, relative to some observable x having had the value x during a measurement, is this projection operator, which projects onto the eigenvalue x of operator x, applied to the state vector, modulo some normalization factor. Which means that it's not possible just to represent the state of the systems that have been measured in terms of their relative states. All that we can do is apply the relative state formalism to everything that the universal state vector represents. And I think the reason for this, as Charles argued as well, is that the Schrödinger picture is not a local formulation of quantum theory. But quantum theory has a local formulation, the Heisenberg-picture. And it's because it allows for one such local formulation that the theory itself should be considered local. That it also admits non-local formulations is irrelevant. Local theories generically admit non-local formulations. All that we care about is that there is a local one underneath it all. So I'll now be presenting some work I did with Deutsch about the relative state formalism in which we translate it to the Heisenberg picture. So in contrast to the Schrödinger picture, the Heisenberg picture consists of evolving Q-number observables and a fixed state vector. In particular, I'll be considering a network of n qubits, each of which separately is represented by a triple of descriptors that satisfy the Pauli algebra and which commute with one another if the descriptors in question are descriptors of separate qubits. So if A doesn't equal B, then they have these commutation relations, which will be important later on for the locality result. In the network, we are only considering the gates at integer times. Sorry, we're only considering the qubits at integer times, and they are evolved forward by gates acting on them. So if we have some general gate, then that gate is implemented by a set of units, by a unitary, which is a function of the descriptors of the network, and the qubits descriptors at time t+1 is that unitary acting on the descriptors at time t. As an example, to get an intuitive sense for what these gates do, you might consider the NOT gate, which, although in the Heisenberg picture it doesn't have a fixed matrix representation because the observables are evolving with time, it does have a characteristic expression in terms of the descriptors of the network. In particular, the NOT gate applied to qubit A is equal to that qubit's X observable. And when that gate is applied to the descriptors, you can see it toggles the Z observable of qubit A, showing that it is a NOT gate, showing that the values of the Z observable become negated. And importantly, this gate, because it's a function only of the descriptors of qubit A, leaves all other descriptors completely unchanged. And that is true in general for gates performed on individual qubits. So if we have some more general operation performed on a single qubit, QA, then the gate for that qubit is always a function only of those descriptors of qubit A. And those descriptors commute with the descriptors of the other qubits in the network, meaning that that gate acting between time t and t+1 will leave the descriptors of qubit B, which is unequal to qubit A, completely unchanged. And it is in that sense that the theory is local, that it satisfies Einstein's criteria. That when we do something to qubit A, it only changes the real factual situation of that qubit. Now, a few words about the Heisenberg state. In the Heisenberg picture, it is a fixed constant. It's fixed so that at the initial time t equals 0, all the qubits Z observables are equal to have the expectation value equal to 1, meaning that the Heisenberg state is an eigenstate of each of these Z observables with eigenvalue 1. And this has two nice consequences. First of all, the state is separable at time t equals 0. And it makes it just a constant. Whether it's non-local, in a sense, doesn't really matter. It's like asking the question, is the number 3 non-local? Well, in the theory, it is just a fixed constant. Of course, there might be situations in which it's convenient to represent the Heisenberg state as a somewhat different state, but in those cases can always be reduced to something of this kind, where the initial Heisenberg state is separable by applying unitaries to the state vector and to the descriptors. So as Charles said, the Heisenberg picture is local. It's also complete. I think Charles has probably said enough about that, so I'll just leave it to the fact that these descriptors can be used to compute any of the expectation values of the network. And what I now want to do is use these descriptors for a model measurement in which one qubit M, which denotes a measurer, measures another qubit S, a to be measured system. And they do this through the application of a NOT gate. So initially, qubit M is in some ready state where the Z observable of qubit S is in a superposition of the values 1 and -1. And through the application of the NOT gate, it evolves into this Bell state, where the values of the measurer being 1 mean qubit S had value 1, and the value of the measure being -1 means the measured system had value -1. The same effect of this gate, written in the Heisenberg picture, is a bit opaque. It scrambles the descriptors as follows, and it is not completely clear how to recover the relative states from this description, whereas I think here it's relatively straightforward. So instead, it is convenient to write the effect of the gate like this, which shows that, can I use the mouse? Yes. In those parts of the multiverse in which the Z observable of the system has value 1, namely, I seem to have lost the mouse. Yeah, so in these sectors of the multiverse, qubit M is left unchanged. Whereas in those sectors of the multiverse in which system S has a Z observable with value -1, a NOT gate is applied to that qubit. And this is exactly what happens in the Schrödinger picture, or seems to happen in the Schrödinger picture. A NOT gate is applied conditionally depending on the value of the Z observable of qubit S. Meaning that we can define the relative states as follows. They are the descriptors multiplied by these projection operators for the observable QSZ. And similarly, we may define the relative descriptors of qubit S as the projection operators for the Z observable of the measure having value 1 and -1. That way, we're considering the measured system relative to the system being measured having a particular value, and the measured system relative to the measure having a particular value. And what is important for the construction is that we can do this independently. I can write down the relative states, these ones, for the measurer, independently of what I do to qubit S. I could have left it unchanged, I could have foliated, so the term that we use in the paper is we foliate a system into relative states, and I could have foliated it differently depending on the physical situation. But I have some freedom to apply these projectors in ways that are independent of each other. And another feature that is interesting to comment upon is that with respect to these projection operators, the descriptors still adhere to the Pauli algebra. So the projection operators essentially play the role of a unit observable in these separate universes, and the systems are still fully quantum in them. They still have algebraic properties of the absolute systems, single qubit gates can be performed on them, etc. And now, the novelty of the theory is that if I take these qubits, Qm and Qs, as well as some environment, which I haven't specified, can be entangled, cannot be entangled, doesn't really matter, it's completely general, and I move them apart, as shown in the animation, and perform a measurement of qubit S using the measure qubit M, then I can foliate these systems into relative states, independently of what is done in the space-like separated region, which is exactly what we wanted. So these things are Everettian universes. They're not really universes at all. They are bubbles existing in finite regions of space, where systems can be written separately of each other, or written in terms of instances. And I think this is something that we should want from the theory. For example, in a different reference frame, so this is kind of a cartoon, the systems on the right side might not have measured might not have performed a measurement at the same time as QE was on the other side of the space-like separated region. There is ambiguity about what now is. It's not Lorentz invariant. And this is not a problem in the current theory. We can decide to foliate these systems independently of each other in these bubbles. So nothing is transmitted from the world on the right to anything on the left of the diagram. So each Everettian universe is therefore represented by Q-number descriptors and are fully quantum, and each such universe is spatially bounded, making them local. That was the end of my talk.
Okay, thank you for the talk. Questions?
Thanks. I have another general question about this picture, following on from the last talk. How should I understand the Pauli exclusion principle in this picture? So electron degeneracy pressure, say, in a white dwarf. That seems like a fundamentally non-local process.
So in the Heisenberg picture, sorry for everyone following online. So in the Heisenberg picture, the explanation for all apparently non-local phenomena is this thing called locally inaccessible information, which is information stored in both systems separately, which cannot be retrieved through either of them, through measurements on one of them alone. And for example, in the teleportation experiment, there was information stored in the classical bit that was traveling from, was it Alice to Bob, which no one could access except for Alice and Bob. They had to use both of their qubits to find that information stored in the classical channel. That's why Charles said that eavesdroppers cannot retrieve it. And in general, that is the explanation for all apparently non-local phenomena. It's always that there's some information stored in both systems, which can only be retrieved through measurements on both of them, not measurements on either of them separately.
Is this a promissory note? Have you actually done calculations that show the exclusion principle works this way, or are you just telling me what you expect will happen?
I guess I'm basically telling you what I expect to happen, but this is referring to the result of the Deutsch-Hayden paper. In the Deutsch-Hayden paper, which kind of is what we're referring to in this formalism, they explained that these apparently non-local phenomena are all due to locally inaccessible information. So anytime that entanglement plays a role in quantum theory, their claim is that can all be reduced to statements about information not accessible through measurements on one system in isolation. Yes.
Okay. I think this usage of locally inaccessible, it's kind of serious weakness. We have two places and we have some mediator and we say, okay, it's locally inaccessible. I think it's much easier to say, okay, the information in these two places where it is accessible. What is usually in science, if something conceptually cannot be measured, it doesn't exist. But my main problem here is that you say this Everettian universes. Everettian universe is not local. It has everything. It's not bounded by space-time. This is completely new story. The whole idea, even for Everett, who has slightly different semantics, his relative states is the whole universe. He might have a relative observer, and in his relative observers, some other places might be in superposition, which I don't like, since I want to put everyone, all macroscopic objects, well localized. In Everett, its own every observer has neat, very well-defined concept for himself, but still, every observer can think about any place in the universe, whatever remote it is. So this concept of a bubble, of space-like separated thing, it's completely new thing. You also have to use some different, completely different language for this.
Okay, so I'll respond to both questions. So there's a sense in which it is new because it's a reformulation of the theory in terms of the Heisenberg-picture. It's a reformulation of the theory in terms of the Heisenberg-picture, and it makes evident that the theory, as we understood it, is local, that we have a local formulation of it. That these state vectors appear to be non-local. I think it's just an artifact of the non-local Schrödinger picture, which I think we shouldn't use. And the other comment about the locally inaccessible information being a weakness, yeah.
There is no concept in Everett universe of specially bounded place. There is no such.
Well, that's why I'm trying to introduce it.
So this is not. Should be different name. This is not Everett universe.
Yeah,
Everett,
yeah.
The whole story. Yeah, you put it here. You call it Everettian multiverse, even multiverse universes. No, every Everettian universe includes the whole space.
Yeah, it's a misnomer.
Not just specially bounded place. By definition, this is the semantics. So you
yeah, I mean, that's why I use the scare quotes. So they're universes. They're not actually, they don't contain everything in existence. They are things in bounded regions.
Also on Everettian, Everett didn't have this concept. There's no such concept in Everett story or in my story, on many word story. This is not the many word story. This is something different.
Well, I think it's just the story of Everettian universes in a local way. And then the other comments about locally inaccessible information being a weakness of the theory, I mean, I think is very comparable to, for example, in space-time, curvature not being observable locally. You can only observe curvature by going through these loops in space-time. That to me is very similar, and I don't think that's a weakness of general relativity either.
Well, as long as you don't call it a Levian universe, it's fine. The question I wanted to ask is different. So you really think of qubits that are separate and so on, but thinking quantum mechanics, for example, of a charged particle, an electron, in a magnetic field.
Right.
In that case, you cannot separate the two things because the speed of a particle depends on the vector potential. For example, you may have a particle moving on a circle with a fluxon in the middle, and even the structure of the Hilbert space, it's not a question of interaction. The structure of the Hilbert space is different depending on the fluxon in the middle. So you cannot separate to say I have a qubit here and a qubit there.
Yeah, so I think that's one of the problems that was solved by Merletto and Vedral in their treatment of the AB effect, where they explicitly show that an electromagnetic field can have local interactions, is local in the same sense that I described here. It satisfies Einsteinian locality. Yeah, I will for that. I think it also partly depends on which gauge you choose. So if you choose a Lorentz gauge. Right. Well, I think for that paper, for that question, I would have to refer you to the paper. I think that's a nice treatment of it.
Yeah. Okay, about 40 years ago, I don't remember this too well, but I read the EPR paper, and I found that quantum theory with no collapse literally satisfied their condition of locality. And I mean, the point was, I just said, well, what's over on the one side, all the thing that just by itself is described by the density matrix here. What's over on the other side is by itself only described by the density matrix. No matter what you do over here, it doesn't change the density matrix. So isn't it true that you can satisfy the Einstein EPR definitions without even going to descriptors? Just do it in terms of the density matrices.
Yeah, I think that's true, but then you run into the problem that you haven't described the system fully. That to make all possible predictions and derive all possible expectation values that the theory produces, you would need the density operator of the full composite system, not just of each of them separately. It's true, yeah.
It's an omission of what Einstein wrote, but they didn't write that you had to know a description of the
Yeah.
whole thing. It's just, could you describe this part in such a way that affecting this didn't? So, I mean, I'm sure if Einstein read my paper, or EPR read my paper, they would probably, oh, well, we misstated things a bit. We really meant this and this. But it seems like if I got it right, literally it satisfied their criterion. But, you know, you might say, well, they wouldn't be happy with it, so maybe we should augment their criteria.
Yeah, so well, I'm very glad to be speaking after Charles, because this is kind of a locality double whammy. And as Charles tried to explain during his talk, it's not, these local density matrices are not complete. We can't derive everything we would like to derive from them. So it's, yeah, I agree with that, yeah.
But I agree that's not.
Yeah, so it's, I mean, Einstein's criterion by itself, you could say, doesn't fully get you, so the local density matrices also satisfy Einstein's criterion, but then there's this additional flaw with them. So I agree with you in that sense that maybe Einstein's criterion should be sharpened.
Yeah, just a quick comment on the interchange between Sam and Lev. I mean, I have read Everett's writings pretty carefully. He never speaks of worlds. He's got the universal wave function, and so I think that clearly does have some universality. But the concept of branches, it's not obvious that it is committed to each branch being a global universe. And we know that he was very unhappy with the terminology used by DeWitt. So it's just a comment on Everett's writings. Lev, if you can cite me chapter and verse where Everett commits to branches being global, I'd like to know.
It's a relative state, and I'm sure that if we have some entangled parts between observer and very, very, very remote part of the universe, clearly Everett will say that this part of remote, it's part of the story, and this is what's relevant here. And here we just put boundary, so even there is some entanglement. This is the whole idea. Q is entangled with one of them.
Well, it could be.
Not, and
I mean,
you don't put it in.
Well, the point of the construction is that you're allowed to, again, foliate. We're borrowing a term from differential geometry to say that you, expressing a system in terms of its different instances is like foliating it. You're allowed to do that on the right, independently of what you do on the left. You could also do it on the left. There's many ways in which you can foliate a system, not all of which are physically relevant. Yes, sir.
Okay, why don't we thank our speaker again?